Good morning. Here's the quick lecture on the concept of center of mass. Now, the center of mass is the position where all of the mass of an object, this pen, oh my, can be considered to be concentrated. Can be considered to be concentrated. The other way to talk about this is to say that it's the balance point of the object. Now, why is this important? It turns out that all motion can be considered by taking motion of the center of mass and motion around the center of mass. So no matter how complicated the motion is, like if I decide to throw a hatchet at the back wall of the classroom, the hatchet is going to tumble and it's going to travel in an arc. Well, the center of mass travels in a perfect parabolic arc, and then anything else is motion around the center of mass. And so we can break complicated motion down into pieces if we know where the center of mass is. Let's see. Let's stutter. Um, there's a couple different ways to find the center of mass. And by the way, I'm going to use CM as an abbreviation for center of mass, not COM, but just CM. And also I'm going to use this symbol right here to indicate the center of mass when I find it in an object. So how do you find the center of mass? Well, the easiest way to find the center of mass is to balance something. So if I had a simple meter stick, and I will do this in the classroom, and I want to balance it, I would probably put my finger underneath the 50 centimeter mark. This is my finger coming out of the page at you. And that means that there would be equal amounts of matter on each side, and the thing would balance. Or you could hang something. So I could tie a string to the center of the meter stick. That isn't anywhere near the center. Huh, interesting. So I tie a string around that, and if I get the string in the right place, there would be equal amounts of matter on both sides, and so it would balance. And so this line where the string is, or the line above the pivot point, that means the center of mass would be along that line somewhere. And then you could also balance it the long way. Put your finger under the center of the end, and you would know that the center mass would be along this point. So for the meter stick, which is essentially a two-dimensional object, now that we have these two axes that we know are the balance points, the balance lines, then you could say where they intersect, that is going to be the center of mass for that object. So to find the center of mass, there's three different things you can do. You can find the center of mass by balancing or hanging an object. By the way, if you just hang an object from a nail, like some sort of weird, let's say you bought some sort of weird piece of art at an auction and it looked like a shark fin or something, and if you just drill a hole in the top of it and hang it on a nail, then wherever the center of mass in the object is, let's say that it's over here somewhere, that's what guesstimate on my part, the whole thing will swivel until this becomes directly below, so the shark fin will actually hang on your wall, you know, in this kind of orientation, so that the center of mass is directly below the pivot point. These are some really spectacularly awful drawings, so there you go. But you can find the center of mass by balancing or hanging, so you know the center of mass is along this axis. If you were to then drill a hole in another corner and hang it from that corner, you could draw another axis and you'd get an intersection. The second way to find the center of mass is by exploiting symmetry. Anytime there's an axis of symmetry in your object, then the center of mass will be along that. That assumes, like this meter stick, I say the axis of symmetry, well, you can cut it in half this way, you can cut it in half the long way. These are all axes of symmetry, and they do produce the center of mass in the middle. But that wouldn't be true if this meter stick was not uniform. If this end of the meter stick was made of a heavier material than this end, then the balance point wouldn't be symmetric. So watch out for symmetry. You need to know that your object is made of all the same material, but it often is the case. You can actually use this to find where the symmetry would be in a human body. So a human body has a head and a torso and a couple of legs. And let's add some arms because people have them. And we have an axis of symmetry that goes this way through our body, more or less. I know internal organs are not exactly symmetrical along that axis, but that means that the center of mass of the human body is somewhere along this line. Now, there is no symmetry in the up and down direction. Our legs are significantly smaller and less volume than a torso, and a head is actually surprisingly heavy for its size. So it turns out that if you do the math and work this out, that the center of mass for a human being is somewhere in your torso, just above your belly button, I think is where it turns out to be. By the way, due to the distribution of mass in a human body, a male and a female of the same height and weight, their center of mass will be in two slightly different positions. Females tend to have less upper body musculature, and when they put on fat, it tends to be in the lower part of the body. So a female's center of mass will often be, for the same height and weight, an inch or so lower than a male's center of mass, which means that for that reason, females are more stable than males. Stability has a lot to do with center of mass and keeping your center of mass over your support points. Okay, so the third way to find the center of mass is the mathematical way. And the calculation that you have to do will take place in this little box. Then we'll do an example. The calculation to find the center of mass is to find the x position of the center of mass. You need to add up, sum, all the individual bits of matter times where they are in the x location. I often write this the other way as mi times xi, and divide it by the total mass of the object. Sometimes this is written, here I'll write it the other way just for fun. So I is an indexing variable. Find all the individual bits of matter and add up that bit of matter times where it is for all the individual bits of matter, and then divide by the sum of all the individual bits of matter, which of course is the total mass of the object. This is a weighted sum or a weighted average. Oh, hey, there's an HTED. Paper, behave. The weighted average, and so there's a weighting factor of mass, so it's a mass weighted average of position is how you would say that. If you need to work in any other dimension, you can do that. This would be the sum of all the individual bits of matter times where they are in the y along the y-axis divided by the mass, and you could do the same thing for the z-axis. Now, if you are a calculus enabled individual, you can see that these sums are probably going to turn into integrals. In other words, if we took infinitesimally small bits of matter and did this process, then our sum would become an integral. And so the x position of the center of mass in a calculus way would be 1 over the total mass of the object times the integral of the position for each individual mass. Now, this is an annoying integral to do. And the reason it's an annoying integral to do is that we are comfortable integrating over spatial variables like along the x-axis, but that's not what this says. This says we're going to integrate all the bits of matter times where they are. So this integral is hard to do on its face, but it's easy if you do a substitution. And if you use the idea of density to morph this integral from mass as the integrating variable to some sort of spatial variable using the concept of volume. Density is mass divided by volume. And that means that density, by the way, the physics people use density as rho, and it means that it's mass over volume, but also it's an individual element of mass divided by an individual element of volume. So this means that dm can be replaced with density times d vol. Okay, so you can change the variables from integrating over m to integrating over the volume. Now the volume, of course, is indicated by spatial variables, right? The height, width, length, these kinds of things. So, and then all you gotta do is find out what the density is. But the density is easy. It's the total mass of the object divided by the total volume. So that would come out front, and then you'd have an integral with density over mass, and then integral of xi Deval. Okay, that's what you would do. We're not going to do this right now. This will come into play in April when we put a lot of calculus into these things. Right now, today, we're going to use these sum versions. So let's do it. Okay. This is the example I usually do in class. It comes to us from Star Trek, the original series. There was an episode where Mr. Spock had to go to his home planet and find a wife or something. I don't know what the deal was, but he managed to get into a fight to the death with Captain Kirk, and they gave them these weapons that had a hemispherical blade. Well, not hemispherical, but a half circle blade at one end, and then there was a long stick, and then there was a heavy weight at the other end for bludgeoning people. Now, I'm going to claim that this object, this thing was 1.5 meters long. And I'm going to claim that this end was 5 kilograms and that this end was 3 kilograms. And we're going to ignore the mass of the stick for now, but we can include it later. Now, if you want to pick up a strange weapon and wield it well, you probably want to pick it up at its center of mass. That way it's balanced and you can swing it around quickly. We can argue about, would you want to leave your hands at the center of mass during the act of striking, or would you want to move your hands someplace? And I think we all have used tools where you got to kind of shift your grip when you're doing the business. So we're going to find the center of mass of this object using the formula. Now, first thing we need to do is we need to pick out where 0 is going to be. And I'm going to make 0 be this end of the weapon. Okay, that means the weapon is all on the positive side of the number line. So we need to find the x position of the center of mass. And it's made up of all the individual bits of matter times their x positions divided by the total mass of the object. Now, because I've ignored the stick, there's really only 2 items here. So there's 2 parts to my sum. One part has a mass of 3 and is located at a position of 0. The other part has a mass of 5 and is located at a position of 1.5, and the total mass of the object is 3 plus 5, or 8. He said, looking around for his calculator, because he knows that he's going to have to calculate something here. Haha. Okay, got it. So 3 times 0 is 0. 5 times 1.5 is what? 7.5. So this is going to be 7.5 divided by 8, and that is a location of 7.5 divided by 8. 9.375. No, 0.9375. So where is that on this picture? Well, we need to go almost a full meter. Not quite, but almost a full meter. So about 2/3 of the way. That's where the center of mass is going to be. Here, I'll put the little center of mass symbol right there. These pens are getting a little aged. Okay, just to show you that this works no matter what you do, let's just say that you didn't want to use that as your coordinate system. Let's say you wanted to use the center of the object as your coordinate system. So here in blue, I'll show that. That calculation would look a little different, because then you would have a 3 kilogram object at a position that was negative 0.75 meters. That is 0.75 meters to the left of your 0. And then you'd have a 5 kilogram object. It's at a position of 0.75 meters. And that would be over 8. Now this is clearly going to give us a different number. So let's do this so that we don't look foolish on camera. 3 times 0.75 equals, so that's a negative 2.25 plus, and 5 times 0.75 equals 3.75 all over 8. Negative 2. So we'll subtract a 2.25 away from that, and so we're going to get 1.5 over 8, which is 0.1875. Okay, now that's a totally different number. So what, the center of mass moved? No, because we're going to measure this far to the right of a position that's in the middle, and that turns out to be the exact same location. So once again, that is where the center of mass is. Now, had we included the stick, we could have done that. We could have included the stick. First of all, we have to know what mass it is. And so let's assume that the stick, 3 kg, 1 kg, 5 kg. If we did that, we could then say, well, look, we're going to cut this into 3 pieces. The blade thing is going to have its center of mass be here inside of it. The bludgeoning thing is going to have its center of mass there, and then this is symmetrical, so let's assign it a center of mass in the center of the stick, in which case using the center as the origin would be a really good idea. So let's go ahead and do that calculation. X center of mass equals 3 times negative 0.75, just like before, plus 1 times 0 plus 5 times 0.75, all over the new mass, which is 9. Okay, so this is going to be the same thing. 1.5, it's because we haven't contributed anything. Good choice of coordinate system. But now we're dividing by 9. So that means that the center of mass is going to shift a little bit, get a little closer to the center. That's 0.166 repeating meters. So now, instead of being a full 0.18 meters to the right, it's now just 0.16 meters to the right. Adding in the stick has shifted the center of mass a little bit. That's how to do center of mass calculations. There are some kinds of problems that we're going to talk about later, but this video has gotten long enough. We'll talk center of mass number 2 soon.